Yeah, so good morning to you all. So I thank Govindan, Kutty and the other organizers for this opportunity to come and speak to you. So this first session is going to be on probability and Bayesian modeling or Bayesian inference. So let me start off with some motivation regarding why we need to look at probability and Bayesian inference for this particular data assimilation workshop. Okay. So I don't really work in this field, so I think I will start with a very simplified problem to kind of motivate this. So we are going to look at a problem where we are trying to track, say, temperature. Okay? So we are trying to track temperature over some instance of time, say like days. Okay? So every day we want to look at something like temperature. So the temperature at the nth day, okay, is Tn, and let's say that we are going to think about temperature as evolving in the following way. So the temperature at day n plus 1 is the temperature at day n plus some in. In is like an increment. Okay, I mean, this is a very simplified model that I could come up with. So what is this? This is a model, right? So we are thinking about temperature using a mathematical model, an equation which says that the temperature at n plus 1 is temperature at day n plus some increment in. So you might be using models like this in your work, right? For data assimilation, things like that.
बढ़िया.
Yeah, so this is like a model, right? So you might be looking at model in your work, and we could maybe, for the purpose of this talk, let us think about this increment as some constant value. Okay, it seems like a good model, at least from where I am coming from. It seems like every day the temperature is going up by 1 or 2 degrees. So it's a simple model to think of. Okay, so I have a question for you, like where do you get this I from? So we are thinking about temperature like this, right? So temperature increments every day by this amount I. Where do you get I from? So have you come across any such problems in, like, when you're looking at your field? Or given this kind of a model for how we are thinking about temperature, and if I say that this In is some constant, how can I find I?
In can be found by giving some weightage to our trial and our observations.
Yes, so you primarily need observations, right? So, or you need measurements, right? So you need measurements. So these measurements, we take measurements using some temperature sensor or something like that. So let us think about these Mn's as the measurement of temperature that we have on day n. Okay. So do you think the measurements will be like this? Will Mn be equal to Tn?
Yeah, maybe if we discard the observations.
Maybe if we discard the observations. Okay, no, you need observations to sort of find out what I is. So you cannot completely discard it, but the thing is that when you take a measurement, this measurement is done using some sensor. These sensors will usually have some non-idealities and things like that, right? And one kind of non-ideality that you can have is what is known as noise. Okay? So you may not get the actual value of temperature when you do measurement. Okay? So if you are thinking about these blue dots as the actual temperature that you have on different days, what you actually get to see or what you actually read out from your measuring device might be these red dots. Okay, so the values will be slightly different from whatever you have. Okay. So this difference that you have between the value that you measure and the temperature that you actually have, some kind of a true value of temperature. That is what we are calling this NN. Okay. So this is a very, as I said, it's a very simplified problem. I think as later in the week you will probably see more general versions of this problem. Okay, where you try to look at a system like this, where you have measurements and try to incorporate these measurements into your model to maybe estimate your model parameters and things like that. Okay, so I is like a model parameter that we have. So, but in this talk, what we are basically trying to do is just two things. Okay, so we are going to think about how to model, to mathematically think about this NN. Okay, so this NN, if you look at it, they are like values that you have, which are deviations from the sort of true data that you have. You cannot really predict what these NN values are. Okay, so they are non-deterministic. You don't know, like on a particular day, what that value will be. Will it be 1 degree? Will it be 2 degrees? You don't know that. Okay, so they are non-deterministic quantities. Okay, there is no way to give a sort of formula or or something like that to tell you exactly what the value of NN is. Okay, but we want a way to think about these things mathematically. So that is one of the first topics that we will look at. You will see that we will, we can use the framework of probability to think about these NNs. Okay? So that is what we will speak about, or that's what we will discuss in the first part of this session. And then we have this other question, like how do we find out I from data? Like I had asked you this question previously. So suppose these are the measurements that you are given. Can you now tell like how I can find I? Is there a very, common sense approach to find I? What can I do if I am given these MNs? So I is like a slope, right? It's like a slope. So can I find out I in some way from these values that I get? So suppose MNs were TNs themselves, how do I find I? So Tn plus 1 is Tn plus I. So I is Tn plus 1 minus Tn. Right? So you just subtract two subsequent, sort of successive temperature reading. Right? If Mn is not Tn, then again this looks like a reasonable thing to do, but maybe you have to do something more to get I. Right? So we need some way of again formalizing this and maybe like think about again a mathematically rigorous way of finding out I from data. Okay. So today what we will be discussing is one way of doing it, which is called Bayesian inference or Bayesian estimation. Okay, but there are other methods also which we won't be covering here. I'll just mention that using a few examples as we go along. Okay, but we will primarily look at a method called Bayesian estimation for this. Okay. So these are the two things that we are going to do. Okay, and the motivation comes from this simple problem. If you have already seen something like this before, you might recognize this as a very simplified version of the sort of underlying system that you have for Kalman filtering. Okay, so it's a very, very simplified version of that. Okay, so whatever we are going to learn can be sort of extrapolated to those kind of situations also. Okay. So primarily we are going to talk about probability for modeling these non-deterministic quantities. How do we do that? That is the first thing that we will do. And the second thing that we will do is to try and understand this procedure called Bayesian inference, which can be used to do things like this. Find out these parameter values, find out these unknowns when you have measurements. Okay? That's what we will do. Any questions here? Okay. So let us start. So we'll start with this introduction to probability. So before we start, let me just give you a brief idea about what we are going to talk about, again in the context of this NNs that we were talking about. Is this phone visible? Can you see? Okay. Yeah. See, so what we have is that if you are thinking about days, okay, on every day we have this actual temperature, true temperature, and we have these measurements, and we are looking at the difference between that temperature and these measurements as this NN. Okay, so if you are thinking about NN, so this is like the value of N1, this is like the value of N2, N3, like that, right? So this is how it looks like. So as I said, there is no way to sort of predict or say give a formula, give a deterministic formula for the value of these N1, N2s and N3s, okay, or NN in general. But we still need a way to mathematically think about this, okay? And so if you are faced with some situation like this, so you don't know what value you will actually observe for, say, this particular quantity N, okay? How can you come up with a way of thinking about this? So you might know that these values, say, can possibly take, say three values, say -1, 1, and 2, okay? So you might think that these are the only values that this can take. Okay? You might think that these are the only values which this can take. So in this case, one of the simplest things you can do to sort of model this is to first say that, okay, I will make a sort of a list or a set of possible values that this quantity can take. Okay? So that's the first thing I can do. Okay? So you have something that is uncertain, which cannot be predicted, which is non-deterministic. So maybe the first thing you can do is to just list down the set of all possible things that can possibly happen. Okay? So that is one thing that you can do. Okay? Now this is by itself not very useful in certain situations. In some situations it's very useful. For example, if you are thinking about a slightly different sort of an example, suppose you are looking at a problem of reliability or something like that. Okay? So suppose you have say an airplane. Okay, and suppose this airplane has like three components, only three components here, okay, for simplicity. And suppose these three components can fail in a multitude of ways. Okay, so you cannot predict how it will fail, what sort of combinations will be there in the failure, but you can still try and make a list of possible things that can happen. Okay, and here that list by itself is very useful because you can do something like a worst case analysis and things like that. Okay, you can do that. But in the kind of problems that we look at, okay, we might be interested in other sort of questions. For example, we might be interested in things like, okay, so if we see this NN for different days, maybe we are not interested in the worst value of N or the maximum value of N. Maybe that's not what we are interested in. Maybe we just want to know the average value of N. Maybe we just want to know the fraction of time N takes a particular value, okay? Things like that. So if we have those kind of scenarios, along with the list of possible things that you can observe or a list of possible values that you can observe, it might also be interesting to associate a chance value with each of the values that this NN can take. Okay? So maybe you say that you are confident that NN is like always 2, or maybe you are confident that it is not -1, or if it's not -1, it is equally likely that it is 1 or 2. Right? So you can think about models like this. And this is in fact what we have in a probability model. Okay, so now we will see more formal way of looking at this. That's okay. Oh. Yeah. Okay. So more formally, what we do is, we just talked about this list of possible values that this NN can take. But more generally, we think of modeling this in the following way. Okay. So we make a set. Okay. So it's a mathematical object. So it's a set. Okay. It's a set of we look at the set of all possible things that can happen. That is called the sample space. Okay. That's called the sample space. In this case, this 1, 2, and -1 sort of constitutes the sample space for n in this simplified example. Okay. Now, the phenomenon that we are trying to look at, okay, for example, here we are trying to think about this NN. Okay. We don't know what its value will be before we observe it. Okay. So we call it a random experiment. Okay. It's like an experiment that we are doing. We don't know what its outcome will be. Okay. So that whole procedure, let's think about it as a random experiment. And the set of all possible outcomes that you can have is called the sample space of this experiment. Okay. So it's just a collection of all possible things that you can have in your in that experiment. We are just making a list of all possible things that can happen. Now, in general, these need not be numerical values. It can be other abstract quantities also. Okay. So we will see an example in a bit. So okay, so this is just some notation. So we usually think about the sample space as this capital omega. Okay, so you can think about in general, you can think about a set like this. Okay, so it's some set like this. So this is omega, and there are elements of this set which are called small omega. Okay, so this is the sample space. So these are some typical examples that you tend to see in, say, if you take a probability book or something. Okay, so a coin toss. Okay, so coin tosses are like bread and butter to probabilists. Okay, so if you take a coin, if you toss a coin, so before the coin lands and you observe what has happened, you don't know what the output of that coin toss would be. Okay, you don't know the outcome of that coin toss. Right, so it's a random experiment. The possible outcomes are heads or tails. Right, possible outcomes are heads or tails. So this head or tail is like what is there in this sample space here. Okay, so there are only 2 points in this sample space, head and tail, okay, like that. If you are rolling a dice, so this is again a sort of typical example that you see. So a die has 6 faces. Okay, so when you roll a dice before the the dice stops rolling, you don't know what the outcome would be, right? So you can make a list of all possible things that can happen, so that in the case of a dice, you can think of it as the value of the face that will come up. So 1, 2, 3, 4, 5, 6, like that. There's another example. So suppose you are positioning a sensor. Okay, so you are, say, randomly throwing a sensor onto some forest area or something. Okay, suppose that forest area is of size or is of area 1 square meter by 1 square meter. So because you are throwing the sensor randomly, before the sensor lands and you are able to localize where the sensor is, you won't be able to know like what that XY coordinates of that sensor are, right? So the sample space in that case is like, you can think about a square here, which is of size 1 square meter, by, sorry, 1 kilometer by 1 kilometer. And all possible points inside it are possible outcomes of this random experiment. Okay, so this is the sample space. Any questions here? Okay. Now, once you have thought about modeling this a quantity like this or a random experiment like this using a sample space, you also define something called events, okay, which are like interesting things that you are that can happen, and you want a mathematical way of modeling that. Okay? For example, like in this case of a dice roll, right? You might be interested in the event that the value that comes up is an even number. Okay? So maybe you have made a bet with your friend that if it comes up even, then you will get some money. Okay? Something like that. So the interesting thing that you are looking at is whether the value that comes up is 2, 4, or 6. Okay? So this is like a subset in your sample space. Okay? So this is like a subset of your sample space. This is called an event. Okay? This is called an event. And sometimes you will need to look at the set of all such subsets that you can have, which is called event space. We won't be really using that here. Okay? But this is what an event is. Okay? The subset of a sample space, that is just an event. Okay, so for example, in that sensor problem, like we had talked about throwing a sensor into this 1 square kilometer area. So in that case, maybe an interesting event is that a sensor lies within some distance from a communication relay. Okay? So you are throwing a sensor, it lands somewhere here, but you have like some communication relay here. So this sensor will be able to communicate with this relay only if it is within some range of this relay. So the interesting event is whether the sensor actually comes and falls here or whether it falls outside. Okay? So here you can think about this as something that you are really interested in. Okay? So when you do the experiment, you are interested in the event that the position of the sensor is within this circle, okay, or in this disk. Okay? So that is what we are interested in. So this is what is called an event. And then you have probabilities. So remember that when we are talking about this NN, okay, so I told you that in certain kinds of scenarios, you might be interested in a chance value for this particular NN. Okay? So you may be interested in saying that, okay, I expect that NN will take this value, or I am highly confident that NN will take that value, like that. So we can model this using a probability function, okay, and it is defined in the following way. So you think about probability as something that assigns these chance values, okay, to events. Okay, so they map events into real numbers. Okay. So if I have an event here, there is a mapping or there is a function that tells me what the chance value of this is. So there is some number that okay, so there is some number that quantifies this. Okay. So this value that you assign to events, okay, is called probability. And we can think about this probability in two ways. Okay. So one is a more sort of a subjective way. So you can think about this value that the function maps to. You can think about it as something like the amount of belief that you have, okay, that the outcome that you are seeing or the event that you are seeing will occur. Okay. So this is very subjective. Okay. For example, you might strongly believe that this number is 2. Okay. Or when you toss a coin, if you are feeling lucky, you will, and you might strongly believe that whatever you have called, say, heads will occur. So this is like a subjective belief that you can have. That is one way to assign probability values to events. Okay? That is one way to do that. We will actually talk more about this in the second part of our session. Another way that you can think about assigning a probability value is to think about this value that you are seeing, that you are assigning here, as something like the long run fraction of time that you get to see this, event. Okay? For example, like if you look at this NN example, so suppose you think about observing noise over a large number of days. Okay? So suppose you are able to observe noise over a large number of days. Then you just look at the fraction of days where you see this value 2. Okay? Now, the next day, if somebody asks you what do you think the chance of seeing 2 is, maybe a reasonable way to answer it is to say that, okay, whatever fraction that you observed before, that is the chance. Okay? Because you kind of maybe you're sort of intrinsically assuming that, okay, that same value will occur with suppose this 2 has occurred, say 99% of time in the past, maybe it will occur again, and this is the chance with which it will occur. Okay? So that is another way to assign probability values to these numbers here. Any questions here? Okay. So we will talk about the probability of an event. Okay, so the probability of an event as probability of, okay, sorry, I used the wrong notation here. So we'll say probability of E. Okay, so these are just some numbers that tell you or which try to model the chance of a particular outcome. Okay, it's not really chance of a particular outcome, the chance of an event. Okay, now there are some rules that these probability values should satisfy. Okay, so one important rule is that if you look at the probability of the sample space, so we are looking at an event which is the sample space. So this is like an always true event, okay, because you know that the set of all possible things that can happen has to lie in the sample space. Okay, so if you are looking at an event which is defined as the sample space itself, then that event will always happen. Okay, and that event will always happen. So that means that, well, it's an always true event, and we are going to take this convention that the probability of that always true event is 1. Okay? So you can just think of this as a convenient sort of normalization that we are using. So if the probability of an always true event is 1, then maybe you can believe this, that if you look at the probability of any other event, its probability value or its chance value should be less than 1. Okay, because for example, if you have a sample space here, okay, and if you think about an event, so this is one event which is A, this is another event which is B. So the probability of this whole space is 1. Okay, maybe it is reasonable to believe that if you look at a subset of that space, its probability will be less than 1. Okay? So if you look at this picture, maybe you can think about this intuitively, that its probability should be less than 1, because it's just a part. Okay? So if you do that random experiment, maybe you will get an outcome that is not in this A. Okay? It might lie here. Okay? So in that case, the probability value that you should assign to A should be maybe less than 1. So this is a convenient normalization, and I think you can sort of remember this property using this kind of a intuitive picture, right? And we will think about probabilities as being greater than or equal to 0. In fact, if you think about probability using this long run fraction of time, you can see that, well, the long run fraction of time cannot be negative, right? Minimum it has to be 0. You don't see the event at all, so minimum it has to be 0. And this is also another sort of rule that probabilities have to satisfy. So what it says is that if you are looking at events, okay, if you are looking at events, and suppose you look at disjoint events, which are just disjoint sets. Okay, so what are disjoint sets? So if you take two sets and if they don't have an intersection, they are disjoint. Right? So suppose you have this sample space, and suppose you have disjoint sets like this. Okay, and you can also look at maybe just 3 of them if you want, leave out this A4. So what this rule says is that if you are trying to look at the probability of these 3 events, okay, that means probability of A1 union A2 union A3, okay. So you're basically looking at the chance, or you're trying to ask this question like, what is the chance that I will get an outcome from this random experiment which is one of A1, A2 or A3. Okay? So it's an event which is made up of the union of A1, A2 and A3. So it can be like if you looking at the dice roll, what is the probability that the number that you get is even or prime. Okay? So you can look at an event like that, right? So, okay, so there the events are not disjoint, but that's the kind of thing that we are looking at. Okay. So if the events are disjoint, then what this rule says is that you can actually compute these probabilities by looking at their sums. Okay. So this is also an important property that probabilities should satisfy. Okay. So if you have these 3 components that we have discussed, the sample space, the events, and the probability function, which gives probability values to events, if you have these 3 components, then you have a complete probability model for a random experiment. Okay? So those are the 3 components that you need to sort of properly model something that is non-deterministic. Any questions here? Okay, so these are some examples of probability values that you can assign. For example, if you are rolling a dice, then the probability of any phase, okay, you can say that it could be like 1/6. So right now you can think of it as some kind of a belief that you have. You strongly believe that all of them are like equally likely to come up. Okay, so but you need probability of this omega to be 1. So in that case, if all of them are equally likely to come up, then they should have equal probability values. So there are 6 of them. So each one should have 1/6, like that. So that is one way to assign probability values. So if you think about that sensor throwing example, so you are throwing the sensor inside some area. So it is, say, equally likely that this sensor will go and fall anywhere. Okay? So if you want to find out the probability that the sensor falls in, say, this rectangle, okay, the probability value that is assigned to this whole area is 1. Okay? So the probability that you can assign to this area would be like the ratio of the actual area of this. So suppose this is length and breadth here, and this is like 1 cross 1. So you will have L into B by 1. Okay? That will be like the probability value that you can assign. Because it is equally likely that any of these points can come up when you throw this sensor. Right? So these are some ways in which you can assign probability values to the outcomes that you can have, to the events that you can have in a sample space. So if you have omega, which is the sample space, okay, the events and this probability function, then you have a proper mathematical model of the random experiment that you are trying to look at. Okay. So there is maybe one thing that I should mention here. Okay. So when you are thinking about a random experiment, so you can think about something like an observation time. Okay. So you do the random experiment. So after this observation time, you get to see the actual outcome. So this model that we are trying to build, right, this sample space, the probability values, the events, things like that. So you can think of that as a model that we are using to think about this random experiment before this observation time. So before this observation time, things are uncertain. You don't know what will happen. So what you are trying to do is you are trying to just list down the set of all possible outcomes which can come. You say that, okay, this outcome might happen with this much chance value or probability value. Okay. So this is sort of the, so we are trying to come up with a model before this observation time. After this observation time, you actually get to see what the outcome of the random experiment is. Okay. You get to see the outcome of that random experiment. So this is what we are trying to model in this kind of a scenario is what that is the kind of scenario which we are trying to model using this probability space, sample space, probability and events. Okay. So any questions here?
Sir, would you like to explain the probability of disjointness by giving a real example like this scenario or anything?
Yeah, so see, for example, suppose you look at okay, so let's look at this case of this dice getting rolled. Okay, see, so each of this we thought of as having an equally likely chance of coming up, right? So each of this we thought of as having a chance of 1 by 6, 1 by 6 like that. Okay. So suppose I want to now find the probability that you get a prime number when you roll. Okay. So what is that event that you get a prime number? So it is the event that you either get 2, 3 or 5, right? 2, 3 or 5. So the event that I am interested in, which is a subset of this sample space, is 2, 3 and 5. Okay. So we are trying to ask what is the probability of this event. We are trying to ask the probability of this event. So what that particular rule, if you try to think about how it will help you, is to give you a rule which can help you find these probabilities. Okay. So this event here is actually the union of 3 events. So this event 2, 3, 5 is the union of 2, the event 2, that means only 2 has come up when you rolled, and or the event 3, which is 3 has come up when you rolled, or 5. So it is a union of these 3 events. These 3 events are disjoint, right? So this set 2 is disjoint with 3. There is no intersection here. Right? This 2 of course has an intersection with this, but these 2 are disjoint. So what this is saying is, what this rule is saying is that this probability you can find by looking at probability of 2 plus probability of 3 plus probability of 5. So which will be half. So it is, half. 1 by 6 plus 1 by 6 plus 1 by 6. Right? So it will be half. So that is what it is to say. Right. Any questions here? Okay. So now when you look at probability, okay, so we will usually be interested in things like this, like finding out probability of some event. Okay. But the main issue would be that finding out probability of some event might be difficult. Okay? So we need to have some formulae, some rules which will help us to find out the probability of some event based on simpler events, okay? Or like what we did here. Okay? So we needed to find the probability of 2, 3, 5. We didn't know that at first, but we could write it in terms of probabilities of some simpler events like this. So there are other kinds of rules and laws and things like that which we can use to do this. Okay? And now we will look at some of those things. So one of the first rules that we will study, and which again we will be using this quite extensively in the case of Bayesian inference in the second part, is something called conditional probability. Okay? So here we are looking at 2 events. Okay? So suppose you have A and another event B. Okay? So there are 2 events, And we are looking at a modeling scenario where we think about observing one event first. Okay? So we get to know that event B has happened. Okay? So once we know that event B has happened, we now want to think about what would be the chance that A would happen. Okay? So that is the kind of scenario that we are in. So for example, suppose you have like again this dice. Okay? So you are rolling the dice. Okay? So suppose someone tells you that the value that has come up. Okay? So somebody, your friend has already seen that, and that friend has observed that the value that has come up is even. But now you want to ask, okay, given that you already know that the value that has come up is even, what is the chance that the value is 2? Okay? So you want to know that. So for example, this is whatever I'm going to say is much more easier. Suppose you know that the value that has come up is even, what is the chance that that value is 3? It will be 0, right? So there is something that you get or some information that you get from this event that has already happened, which is changing your probabilities. Okay? So if you did not know that the value that had come up was even, what is the probability or what is the chance that the value is 3? It is 1 by 6, right? So like we saw that. If you don't know that, if you don't have any information regarding that, then the best thing that you can say is, well, okay, it is equally likely, so maybe it is 1 by 6. But once you know that this has happened, that it is even, then it changes your probability, right? So this notion of conditional probability helps us to quantify that. So if there are two events A and B, then you can think about, well, what would be the probability of A given that B has occurred, and this is usually denoted like this: probability of A vertical bar and then B. Okay. This conditional probability is given like this. Okay. It's the probability of A intersection B by probability of B. Okay. And this is true if probability of B is greater than 0. Okay. Now, why this rule is reasonable to believe? Like, you can actually think about this using that, we thought about probability using the long run fraction of time that something is happening, right? An event is happening. So you can think about that to sort of get to this. So let's again think about this dice getting rolled. Okay, so you are rolling dice many times. Okay? You say rolling it 1,000 times or so. So every time you roll it, you can observe whether the value that has come up is even or whether the value that has come up is odd. Okay? So it's either E or O. So suppose you roll it many times, what you might get to see is, okay, the value is even, then odd, then it is even, then it is again even, then it is odd, like that. Okay, it's like that. So this is like the event B that we are talking about. Okay, so we have already seen whether it is even or odd. Okay, so that is this. Now we also get to see the exact value of that dice. The face value which has come up. Okay, so maybe it is like 1 here, maybe it is 2 here, maybe it's again 1 here, it is 3 here, it is say 2 here, 3 here, like that. Okay, so it goes on like that. So the probability value that we are interested in, which is like probability of A given that B has occurred, is something like, given that this E has occurred, okay, given that this E has occurred, what is the probability? Oh, so this will never happen, right? Sorry. So I seem to have messed up that. Yeah. So given that the event E has occurred, what is the chance that you get to see a particular value, say 2 or 4 or something like that, right? So how do you find that? So you know that E has occurred. So what you will do is you will only look at those times where E has occurred. You won't even look at the times where this O has occurred. And for only those times that E has occurred, you are trying to find the fraction of time a particular value has come up. Okay? So that is like, say, suppose you are interested in this value 2. So you'll see that once E has occurred, or given that E has occurred, 2 has occurred 2 times out of 3, right? 2 has occurred 2 times out of 3. So that is like the conditional probability. Okay, so that is the conditional probability. And how are you getting that? You are actually counting the number of times E and 2 has occurred. So that is what this A intersection B here is doing. Okay, and then you are just finding out the fraction of the times out of the times that E has occurred where both E and 2 has occurred. Okay, so that is why you have this probability of B in the denominator. Okay, so this is how you can define conditional probability. And okay, and again, like if probability of B is 0, then you basically say that this conditional probability is undefined. Okay, and this conditional probability is very useful for us in answering questions like this. So given that something has occurred, once you know that it has occurred, you can ask for what is the new probability, or what is the how does the probability change if you have this new information that some event has occurred. Okay? So that is what conditional probability is. Any questions here? Okay. So yeah, so we just did this example. So suppose you roll a fair 6-sided dice like what you had here. So what is the probability that the face is 2 given that the face is even? Okay, so that is what is that probability? Can you find that out? So you know that it is just like what we did here. Okay. Tell me. So you can just try to do this. So what is the probability that, so what are the events A and B here? So A is like the event that the face is 2. Okay. B is the event that the face is even. Okay. So what is the chance that the face is even? 1 by 2, right? So that again you can compute using something like that. So instead of this probability of 235, you can look at probability of 246. So that is like 1 by 6 plus 1 by 6 plus 1 by 6. So that is half. Okay. And what is the probability that you get 2 and it is even? That is 1 by 6, right? So if it is 2, you know that it is even. So A intersection B is just the even that it is 2. So it is 1 by 6 by 1 by 2, right? So that is 1 by 3. Okay. And you can see that this probability has changed, right? This probability is not 1 by 6. So given that you know that it is even, the probability has changed. It has changed from 1 by 6 to 1 by 3. The probability has actually increased. Okay, so this is conditional probability, and this conditional probability is something that we can use to derive this or get to this formula. We will think about this as a formula that says that if you want to find the probability of some event B, then you can find that probability using a rule like this. Okay, so what this rule says is that if you have a set of disjoint events A1 up to AN, okay, then you can find the probability of B as summation of probability of AI into the probability of B given AI. Okay, so this is called the total probability rule or total probability theorem. This is again a very useful result or formula that you can use to find out probability of some event. Okay. So can you think of any scenario where something like this might be useful? Okay, so maybe let me think about an example here. So suppose you are again looking at this this temperature sort of a problem. Okay, so suppose you know that if say there is rain, okay, then the temperature values can be say 10 15 or 20 degrees centigrade. Okay? Suppose it's like that. So if there is rain, then the temperature can be 10, 15 or 20, and given that there is rain, the temperature values are 10, 15 and 20 with say chance 1 by 3, 1 by 3, 1 by 3, okay? Something like this. So if there is no rain, okay, if there is no rain, then the temperature values can be 15, 20 and say 25. Okay, again say with probabilities 1 by 3, 1 by 3, 1 by 3. Okay. So what is the probability that you have a temperature of 15 degrees? Okay, so this is the kind of problems that we can try to think about using this total probability rule. So here you can see that we are thinking about kind of a sample space. You can think about a sample space omega. Okay, you can think about a sample space omega where there are these outcomes which correspond to rain and the temperature value, okay, something like this. So what we are actually given are, you can think about something like conditional probabilities here. Okay, so you are given that the temperature is 10, okay. The probability that the temperature is 10 is 1 by 3 given that there is rain, okay? Something like that, that is what is given. So if you also know the probability of rain, okay, maybe it's like say half and half here, okay, you can see that you can use a rule like this to easily compute the probability of getting 15 degrees, right? So sometimes this information about conditional probabilities will be useful, okay, will be much more useful than directly computing the probability of this B. Okay, so that is where this kind of a rule might be useful. You can try to think about how to derive this particular result. It is actually not very difficult. In fact, if you go back here, okay, so you had this rule here. You can think about whether it is possible to use this to come up with that. Okay, so there are also these disjoint events that we are talking about here. Earlier also we had disjoint events. Okay, so see if there is a connection here. Okay, so in fact, if these are disjoint, then if you take the intersection of B with them, okay, so that is B intersection A1, B intersection A2, like that, then they are also disjoint. Okay, so maybe that will help. That's a clue which you can use to try and get this. Okay. Now we had seen these conditional probabilities. Conditional probabilities, once you know about them, it becomes easy to talk about something called independent events. Okay? So two events, A and B, they are called independent, and I think this is a much more easier way to sort of think about this. If the probability of A given B is just probability of A. Okay? So that basically means that even if you know that B has occurred, it doesn't really change the chance values of A. Right? So A is in some sense independent of the fact that B has occurred. Okay? So that is one good way to think about this. So here, like, for example, suppose you are thinking about, say, two independent dice getting rolled. Okay, so two physically independent dice are getting rolled by, say, two different people. Okay, and there is no way that these two processes are related to one another. Then you can think about the event that the first dice will turn up heads. Will have a value, say, 2. And the event that the second dice will have a value, say 3, they are like independent of each other, right? Because the underlying physical processes are independent. So there are many places where this kind of an independence assumption will be useful in modeling. In fact, when we usually start out with modeling noise and things like that, we will actually think about noise at say in this case, this NN is like a measurement noise that we had. We can think about noise at different days as being independent. Okay? I mean, that's like a first cut model that you can have. Okay, so yeah, so that is what is independent events. Okay, so what we have covered up to now, we have talked about this random experiment. The random experiment has a set of outcomes. The set of outcomes is put into this set called the sample space. Then you have events which are defined on the sample space, and then you have probability values which try to encode this this belief or this chance value that you are placing on these outcomes, right? So you think that some outcomes may occur. Well, this is the this is your belief that it might occur. That is encoded by these probability values. So when we are talking about random experiments using this kind of a sample space, events, and probability, this tuple, the sample space can be quite general. Okay? So in fact, there is, I mean, if you are thinking about the sample space, the elements of this sample space need not be numbers. They could be anything. Like for example, if you are tossing a coin, it is like heads and tails. There is no numeric value which is associated with it. Okay? But in many cases, what happens is that the like for example here, when we are thinking about measurements and things like that, the actual values that we deal with are numbers. Okay? The actual value that we deal with are numbers. So it makes sense to sort of think about, say, how to use numbers to model outcomes of an experiment. Okay? So or is there a way to take a random experiment and suppose you want to think about the outcomes using some numerical values which you can then manipulate using your usual rules of arithmetic and things like that. So when you are faced with those kind of situations, it becomes more reasonable to think of modeling this outcome using numbers. Okay? And you can think about random variables as a way to do that. Okay? So random variables are simply a way of mapping this sample space into numbers. Okay? For example, if you take this coin toss, right? The coin toss, the underlying sample space has heads and tails. They are not numbers. Okay? But suppose you now say that whenever you get a heads, you will get 10 rupees, or whenever you get a tails, you will get minus 10 rupees. Okay? And now you can think about a situation where you are tossing like 10 coins and you want to find out the total amount of money that you have according to this rule. Like if it comes up heads for any coin, you will get 10. If you get tails, you will get minus 10, something like that. So here you can see that you have a random experiment. The outcome of that random experiment is mapped into a number, and then you are doing arithmetic on those numbers. Okay? So in fact, because you are mapping it in numbers, you can do arithmetic on it. Right? So how can we do this mapping? So that is what is done by these discrete random variables. I mean, that is what is done by random variables. So we can start off by looking at what are known as discrete random variables. And in fact, when you come to modeling, random variables are what is really important. Okay? Usually we don't really talk about the underlying omega and probability and all that when we think about modeling. We usually start off directly with random variables. Okay? So random variables are formally defined as functions which map your sample space into the real line. Okay? So basically, if you have the sample space, every point in the sample space you take and assign it some value on the real line. Okay? So it just means that you assign some numerical values to every point in the sample space. Okay? So that is all you do. If the set of values that you finally get, okay, if they are discrete, okay, for example, if they take only values like 0, 1, 2, 3, like that, then you call this function, which is mapping sample space to R, as a discrete random variable. Okay, so the discreteness arises from the fact that you have discrete values here. On the other hand, if the number that you maps to can be any number, any real number, you call it a continuous random variable. Okay, and there are also combinations of discrete and continuous random variables and things like that. Okay? But basically, you just think about this function which maps the sample space onto this real line. That means it just assigns real numbers to it. The set of real numbers that you assign are discrete, you call it a discrete random variable. Okay? So even though we say that it is a variable, so usually when you think about a variable, you think about something that is scalar. Okay, it's a scalar valued quantity. This object is not, it is not a variable in the usual sense. This is actually a function. Okay? A random variable is actually a function. It is not a scalar valued quantity. Okay? It is mapping every element of the sample space to values on the real line. Okay? But it is, if you think about it as a mathematical object, it is a function. Okay? It's not a variable like in the usual sense that we use. Okay, so let's think about some examples here to understand what this is. So suppose you think about, like we are talking about this coin toss. So suppose I have a coin, or suppose I have 10 coins and I toss it. Okay, and suppose I think that the coin will come up heads. Okay, with some chance p, which may not be like 50%. Okay, so that p is called the bias of the coin. Okay. So suppose this is what I have. So I have 10 tosses of a coin, and x is the number of heads that I have in the 10 tosses of the coin. Okay. So here, in order to understand what x is and how to think about x as a function that is taking omega to r, the sample space to r, let us try to understand what omega is in this case, what the sample space is in this case. So in this case, what do you think the sample space is? So we basically have a experiment where we are tossing a coin 10 times. Okay, where we are tossing a coin 10 times, or we are, say, tossing 10 coins, right? So what are the possible things that you can get when you toss a coin 10 times? So you can get things like 10 heads, or you can get 1 head and then 9 tails. Okay, or you can get 2 heads and 8 tails. Okay, so you can have all these things, and you can also have all kinds of combinations, permutations here, right? So you can have the heads coming second. Okay, you can have all those kinds of things. Okay? So in fact, if you think about it, there are 2 raised to 10 possible such sequences, okay, that you can have as the outcome of this random experiment. Okay, because like there are sort of, you are doing something 10 times, and each time you do it, there are 2 possible things that can happen. So the total number of outcomes that you can have is 2 raised to 10. So you have a very big sample space with 2 raised to 10 such points in it. Okay, so these are like your small omegas. Each outcome is a sequence like this of 10 heads or tails, okay, like that. So this is your sample space, and what we are saying is x is the number of heads that you can have in 10 tosses of a coin. Okay. So what is this x doing? So x is taking a point here, okay, and it is counting the number of heads that you have here. For example, if this point here corresponds to h like that, all heads, then this is mapped into the value 10. Okay, so that is what this random variable is doing. If you had, say, another point here, okay, which only had 8 heads and 2 tails, okay, so this point will be mapped into 8. Now, suppose the 2 tails here occurred in the very first 2 coin tosses, then that is one thing. You can also have another such sequence here with 2 tails and 8 heads. Maybe the 2 tails occurred at the very end, right? So that is also mapped into the same point here. So this is what the random variable is. It is taking points in the sample space. It is taking points in the sample space and then mapping it into the real line. Okay, this is what the random variable is. So we might be interested in just this value, that the random variable takes. Okay? So for example, when you do this experiment, right now, whatever that is interesting to us would be to just think about the number of heads that will come up when you toss it 10 times. So these values would be what are really interesting to us. This underlying sample space is right now not interesting to us because we are just looking at this number. Okay? And that is exactly where thinking about that value that you are seeing as a mapping that is coming from this underlying sample space is useful. Okay? So we will use this mapping with the understanding that, well, it is actually taking this underlying sample space and mapping it into some values here. And these values are what we actually observe. Okay? That is what we will use when we go in for modeling something like this noise, okay? Or in other cases. Okay, so maybe you can think about this another example. So suppose you want to look at the number of tosses until the first head happens. Okay? So you have 10 tosses of a coin. Let's say, we can simplify it. Think about a case where you have 10 tosses of a coin. You are looking at the number of tosses until the first head. Okay? So how will that look like? What does that map look like? So again, a sample space will look like this, right? Sample space will look like this. And you can just see, like for example, if you look at these sequences, they all have heads in the first coin toss itself, right? So they are all mapped into 1, okay? And if you had something like TH and then something, they are all mapped into 2, right? So this is the number of tosses that you have till the first heads appears, okay? Something like that. So that is another random variable. Okay. Any questions here? Yeah. So suppose we have a coin, okay, and when you toss a coin, right? Usually we say that the coin is equally likely to come up heads or tails. Okay. So this is what is called a fair coin. But sometimes you can think about having a coin where you say load the coin on one side, maybe you give it some additional deposits or something like that, so that when you toss, there is more chance that the coin will sort of only land on one side. So maybe it will only land on heads. Okay? So so there are various degrees to which you can do it. So this P captures the fact that the chance of it coming up heads is something different from 50%. So it is like the probability of the coin coming up heads is P. So that P is not 50 or 0.5. Okay, like. Okay, so these are some examples of discrete random variables, and here we are basically thinking about discrete random variables using this definition that it is a map from the underlying sample space into R. And so now the thing is, we have a mechanism to think about the outcome of a random experiment using this set of numbers, okay, using this set of numbers. And so when you are thinking about modeling problems, like for example, when you are thinking about modeling this measurement noise and things like that, we are actually dealing with numbers. Okay? So there we can actually think about these numbers as, well, values that you get to see from a random variable. Okay? Now again, there should be a way to quantify, well, what is the chance that you get to see a particular value from a random variable. Okay? So this is intimately connected with the probability that we had studied before. So we talked about probability of events, right? Here, for random variables, you can think about that probability as being sort of transferred from these outcomes that you had here to these values. Okay? For example, if this particular outcome had some probability, okay, so suppose it had some probability, say 0.1 or something, and suppose that outcome is uniquely mapped to some value here, then you can say that the probability of the random variable taking this value is also 0.1, right? So now this whole probability that we had defined on this on the events here can be thought of as being sort of pushed into a probability that you can define on these numbers. Okay? And the probability that you define on these numbers, okay, if this is a discrete random variable, that means it's only taking discrete values, that is called a probability mass function. Okay? So the probability mass function is just the probability that the random variable takes a particular value, okay? Takes a particular value, small x. And we will say that it is like some px of x, that is the notation that we will use. And it is, it is related to the earlier probability that we had seen, okay? So the probability that a random variable takes a value small x, okay, so can be thought of as something like this. So you think about this case where, we had this value 8. Okay? So in our previous discussion, we said that there are like 2 points here that map to this value 8. Okay? So what we will try to do is, we will try to find all the elements that you have in the sample space, which are such that they all map to the same value under this random variable x. So x is a function, right? It is taking points from here and assigning it values here. So let's think about this set here, all of which have the property that x will map them to the same value here. Okay? Now this is a subset of the sample space for which you can define a probability. Okay? Now that same probability value you can assign to this number here. And that is how you get the PMF. Okay? So in fact, that is what is written here. So the PMF, the probability mass function, is just the probability that the random variable takes a particular value. And that is just the probability of the event. And that event is now defined in this special way. So the event is the set of all outcomes. It's a subset of the sample space with the property that the function, random variable function, maps those outcomes into the same value x. Okay? So that is how you define the PMF. And then the PMF satisfies some properties, like the PMF has to be greater than or equal to 0, and the summation of probabilities has to be 1 and all that. Okay? Okay, so this will directly lead us to something called probability distributions. Okay? So which is again something that is very important in modeling. So the PMF is one way to talk about the probability of random variables taking a particular value. Okay? So you can also equivalently talk about distributions in terms of what are known as cumulative distribution functions and complementary cumulative distribution functions, which are just the probabilities of, instead of saying that look at the probability of the random variable taking a particular value, you look at the probability of the random variable taking values less than or equal to something. Okay? So that is the cumulative distribution function. And if you look at the probability of the random variable taking more than a value, that is the complementary cumulative distribution function. Okay? Now, there are, okay, so maybe we'll come back to this example here and try to think about how we will use random variables to model this. So suppose we take this measurement noise here. Okay? This is the temperature measurement noise that we had. Now, we are observing this noise at different days, and we are seeing these values, -1, 1 and 2. Okay? Now, if you want to think about it as a random variable, we can actually forget about all this sample spaces and things like that and directly try to think about it as a random variable, taking some values with some PMF, with some probability mass function. So let us try to see how we do that. Okay? So here when we look at this example, maybe the set of values that you get to see for this noise, maybe it is only -1, 1 and 2. Okay? So every time, every day when you look at it, you only get to see these values, -1, 1 and 2. Okay? So if that is so, then you can think about this noise, this measurement noise, as a discrete random variable, because it's only taking values from a discrete set. That discrete set is -1, 1 and 2. Okay, it is -1, 1 and 2. And you can think about giving a probability mass function, okay, some probability values to seeing these -1, 1 and 2. Okay. So what do you think those probability values could be? Is there a natural way to assign those values to this? So again, you can look at the long run fraction of time. You get to see -1, you get to see 1, you get to see 2, and assign it to these values that the random variable takes. Okay, so maybe what happens is that you get to see this -1 value 0.3 fraction of time, and you get to see this 0.5 fraction of time, and you get to see this 0.2 fraction of time. Okay? So this is the PMF that you can have. Okay? So this is how you basically build up a random variable model for a particular case, like this measurement noise here. Okay? So you just look at the set of values that you are observing. If it's a discrete set, that's well and good. Then what you do is you just look at the fraction of time you get to see a particular value. That fraction you assign as the probability mass or the probability value to that particular value of the random variable. So this is the PMF, the probability mass function. Okay, this is the probability mass function, and these are the values that the random variable takes. Okay, these are the values that the random variable takes. Now in general, when you look at a problem like this, the set of values that the random variable takes can be quite large. Okay? So it may not be as simple as -1, 1 and 2. Maybe it can take like all possible say numbers, integers, okay? Or say all integers between say some 0 and 40, okay? Something like that. Now when you are thinking about assigning these probability values, say to a random variable that can take say all possible integers or a large set of integers, then you have to find out the fraction of time the random variable takes, or you observe a particular value, and that value, that fraction of time, is what you assign as a probability mass function or probability mass value. But instead of that, okay, there is another sort of way to describe the random variables that you are seeing, which may not always work, but it is something that you can always try, which is by trying to see if some standard probability mass functions can be used to describe these values that you are seeing, this long run fraction of time that you are seeing a value. So there are some standard random variable distributions that we use. So these are some examples where we have discrete random variables where we have these standard distributions. What these standard distributions basically give you is a kind of formula for the probability mass function, which is parameterized. Okay? For example, if you have a binomial random variable, what that means is that there is a formula which is parameterized by two quantities. Okay? So you have a parameter n and a parameter p for a binomial distribution. And what this is saying is that this is the distribution of a random variable which can take values in 0 up to n. Okay? These are the possible values that it can take. And the probability of this random variable taking a value x is given by some formula like this. Okay. So as you can see, this makes the job of describing the PMF very easy, because you just have to specify two things, n and this p, and you get the PMF value for all possible values of x. Okay? And x lies between 0 and n. It also makes the job of finding out a PMF easier, okay? Because what happens is that suppose you want to look at data, okay, like this NN here, and you want to say describe it as a binomial random variable, then what you have to do is to make sure that you find N and P such that this formula that you get, which gives you the PMF, matches the long run fraction of time you get to see a particular value for X. Okay? And there are ways to find out N and P such that that matching happens. Okay? So that is what standard distributions are, and there are also many examples for such standard distributions. Here I have listed out just two others, geometric and Poisson. Okay? And these are like if you try to plot these PMF values as a function of the value that the random variable can take. So these are typical examples of how the distributions will look like. Okay? And when you have a random variable, there are ways to summarize the random variable instead of looking at the complete distribution. So this is one simple summary, simple way to summarize a random variable. This is called the expectation of a random variable. The expectation just captures something like the mean value that the random variable can take. So that means if you take, say, this example where you have NN, if you try to average out the values that you get to see, so you got the value N1 here, N2 here, N3 here like that, you take an average, okay, of those values, and that average is going to be approximated by this function called the expectation, which you can define like this. So the expectation is just like the mean value that you can have for the random variable. Okay, so I think this slide should be shared with you, so maybe you can try to go through some of these questions just to understand it better. And you can also summarize random variables using other summary statistics. Okay, so these are called summary statistics. The mean is one. You would have probably heard about something called the variance before, okay, which talks about how much the random variable's value, the values that the random variable takes, is expected to deviate away from the mean value. Okay? So a random variable with a large variance means that, well, its mean value might be 0, but when you actually look at the random variable's value, it might be away from the mean. Okay? So you may not get the value 0 again and again when you see the random variable. And there are also other things, like for example, if you look at expectation of the random variable raised to some power, okay? So that is called the nth moment of a random variable. So these are ways to describe or summarize the random variable without giving the whole expectation, without giving the whole distribution. Okay, so let me just skip this. Right, so we talked about multiple events before, right? So we talked about A and B, there are two events like that. Similar to that, you can talk about multiple random variables also. Okay, so if you have like a sample space here, you can think about two functions. Okay, so X is one function which is mapping points in the sample space to the real line. So that is one random variable. You can also have another function that is taking the same points but mapping it into possibly different values. Okay, so that is another random variable. And when you have two random variables, okay, you have to talk about the joint probability distribution of those random variables. Okay? So this is important because like you might be interested in questions like, okay, what is the chance that you get to see a value 10 for this random variable but a value 50 for another random variable. Okay? So the joint probability mass function gives you that probability. Okay? And it is denoted like this. Okay? And again, like in the case of events where we talked about conditional probabilities, here you can talk about conditional probability mass functions. So here again, the idea is similar to whatever we had for conditional probability before. You see one event first, and then you are asking, okay, what is the probability of another event, given that you have already seen this other event which has occurred, right? So similar to that, here we are talking about this using random variables. So suppose you have seen one value, okay, taken by a random variable, say y. So suppose you have seen that y has taken a value small y. Then you can ask, okay, based on this information, does the probability of the other random variable x taking a value change. Okay? So that probability is again, I mean that's what is defined here. This is called the conditional probability mass function. Okay? So for example, you can think about again going back to some maybe an example like this. So suppose you had this this noise here. This noise might actually be influenced by the temperature around it, right? Usually when you have a sensor, the sensor characteristics depend on ambient temperature and things like that. Okay, so you can think about asking the question of like, okay, suppose yesterday's temperature was say 10 degrees. Okay, so you might expect that today's temperature is maybe near that. Okay, so then you can ask, okay, what is the probability of having a noise value, measurement noise value of say some some small n, given that yesterday's temperature had this value of say 15 degrees. Okay? So those are the kind of scenarios where you will need a conditional probability mass function like this. Okay. So I'm just going a bit fast because I think our time is almost up, and we will need some of these things in the next session. Okay. So we talked about independent events before. Similar to that, we can have independent random variables. Okay, again the same intuitive sort of definition. So if you have independent random variables x and y, then the idea is that even if you knew what value y had, it doesn't really change your probability. Okay, so that is what independence means. Okay, it's very intuitive, just like what we had before. Okay, so we talked about discrete random variables here, which take points in the sample space and map it into points, discrete points here. Similar to that, you can have continuous random variables. Okay? So continuous random variables, the only difference is that the points are mapped into a continuum. Okay? So you could have an interval of values here, or it could be the whole of the real line. Okay? So that is what a continuous random variable is. And when you have continuous random variables, you can again talk about the probability of the random variables taking a value, but it turns out that if you are talking about the probability that a continuous random variable takes a single value, then it is kind of that probability is zero, because the space is continuous. So if you are asking for the probability of a single value being taken, okay. For example, if you think about looking at the random variables outcomes again and again, the chance that you or the fraction of time you get to see a single value will be zero, okay, because the values will sort of change. I mean that's the intuition. So what you can think of is instead of looking at the probability of a single value, you can look at the probability that continuous random variable takes values in a small interval, okay, or an interval from A to B. And you can think about a density function here, which you can integrate to get this probability. So this density stands in for the probability mass function which we had before. Okay? So instead of using probability mass functions, once you come to continuous random variables, you have to talk about a probability density function that if you integrate over some interval, you get the probability of the random variable taking values in that interval. So that is the difference. There are again some properties that this density function needs to satisfy. And there are some examples for continuous random variables. I think this is probably something that is very commonly used in whatever you are probably doing. Yeah, I'll just stop. Okay. So this is a very common distribution. This is again a standard distribution that you use to describe the probability of a continuous random variable, which is called the normal or the Gaussian distribution. And it basically says that the density has a particular form, which is given like this. Okay, so you might recognize this, like you might have used this before, especially when actually modeling quantities like measurement noise and all. Okay, so similar to multiple continuous random variables, you can also have discrete random variables and things like that. So what I'll do is I'll stop here. We will again start with Bayes rule, and we will use that for Bayesian inference in the next section. Yeah. So any questions here?
Sir, you mentioned that expectation of a discrete random variable is the mean of the random variable.
Yeah, expectation is, I mean, you can think of an expectation as a formula that closely approximates the average of the values of the random variable that you will see.
So, can we only say that the mean of the random variable? What is the justification of using this new term, expectation? Is it because of random nature of the variable?
Yeah, so I mean, we have some experiment, the outcome of which is random. So we don't know what its value will be. It's not a deterministic value. So when we say do the experiment multiple times, you get to see different values for it. You will get to see different values for it. So one way to sort of summarize the values that we are seeing is to take a average of that. Okay, and that average, well, it turns out that if you are averaging only for a finite number of values, that average is also random. Okay, but the expectation that we are finding using that formula, that is a deterministic quantity, and the idea is that if you do this averaging for a very large number of samples, then that average and that expectation which we find are going to be like close. Okay. So the expectation is just, yeah, you can think of it as some new terminology that we are using for that particular formula that we have, which is going to give you a deterministic value.